Hi guys, in the previous video we did just some stuff with cochain complexes. I'm going to, in this video, talk about some things that you can do with derived categories. So let me do some fun example. Okay, so again in this video we're gonna fix A as an abelian category. Okay, and then we're gonna identify objects in A with complexes by concentrating them in degree 0. So when we take an object in A and we say we view it in the derived category, we're really saying we view it as a thing where it's a complex where everything's 0 except for the piece in degree 0, and then the maps are 0. All right, so okay, so let's take an extension, right? Let's recall that we have extensions. So an extension of, let's say, an object H in our category by another object V. So this thing is a sequence. This is an exact sequence so we have the vertical part, and then we have E, H, 0, and then it goes on. Okay, so this is a complex, okay? But here, this is exact, so the image in the image of this map is the kernel of the next, so this is exact. Okay, and so in particular, because it's exact, for example, all the cohomologies will be 0. Okay, so all the HIs in an exact sequence are 0. And okay, so this is something that we have. And recall that to these things, there's this X I of H and V. So this is extension of H by V. So X1, let's say X1. So this is the first derived functor of HOM of so HOM in the abelian category from H bullet. So like this. Applied to, so this thing applied to V. Okay. Okay, so this is one way of doing this. So this was defined to be this thing. And so there's a correspondence between these extensions and these guys here, this group. Okay, and you can actually give these a group structure. I think that was worked out by Kaplansky. I'm not sure. I remember someone worked this out, right? That there's a group structure you can put on these things here, and then that group structure will correspond to the group structure here. All right. So okay, so now here's my claim. Okay, so the claim is that in the derived category, HOM, so morphisms from H to this one are going to be correspondence with X1 of H and V. So extensions. Okay, so there's going to be an isomorphism like this. And more generally, HOM from H to Vn are going to be in correspondence with these higher X of H and V. Okay, so this is pretty cool, right? Because it's like now we're saying that like these cohomology functors are actually represented by something in the derived category. So these things are HOMs. The HOM is in this derived category here. Okay, so this is pretty cool. Okay, so we will construct. So what we will construct. We won't give the whole proof. We'll construct a map from X1 of HV to these HOMs V1. Okay, in the derived category. Okay, and now to do this, I'm actually going to use derived categories. Okay, so I want to construct this map. So what we're going to do is we're going to first take an extension. So So fix an extension, 0 to V E H 0. So this is, maybe we view this as an infinite complex. I'm not going to write the other parts out. Associated to, say, a class in X1 of HV. All right, so we have this now. Okay, so we're going to have these two things here. Okay, so now let me write down something. Okay, so I'm going to write down H. Okay, H is just an object in A, but remember when we want to view it in the derived category, right, or as a complex, right, we just kind of extend it, right, we make it this stupid complex here. Okay, so we have this complex, and then its cohomology is concentrated in degrees 0, and its cohomology at H0 of this complex will be H, and so this is the degree 0 piece again. Okay, I'm going to write down another complex. The other complex is going to be here, where we just take this vertical part, and then we stick it into E, and here we're going to write 0. So we forget that last part here. Okay, so here, so for this complex, let's remember that H0 is equal to H, and HI is equal to 0 otherwise. Okay, also note that this map here induces a nice map here. Okay, and we have this 0 map here. Okay, but let's look at the cohomology here. So the cohomology here, we have H0. Okay, so let's H0. H0, well, this is the kernel of this map, so that's Z0. And then we have the image of this map, So that map's injective, okay? So so this top one is E, and this one here, this is the image of this. So I guess if we identify this as a sub-object here, so then we'll just say that this is V, okay? And this is naturally isomorphic to H. So this is isomorphic to H. Okay, I guess we can see that HI, so these are 0 for I not equal to -1. This is clear because they're all zeros everywhere, and the HIs are subquotients. But H minus 1, okay, I claim that is also 0. Here, the kernel of this map, well, there's nothing. This map's injective. This is an exact sequence. So this is a monomorphism. Okay, so not necessarily, I guess, injective. I guess we should say monomorphism since we're working in an abelian category. But we have this map here, and it's 0. Okay, so here we have this map, okay, and this map's the 0 map, this map's the 0 map, and their first cohomology, let's see. Oh, so did I compute the first? So the 0th cohomology, sorry, the 0th cohomology is H here, this is H here. So this is a quasi-isomorphism. This is a quasi-isomorphism in the derived category. This is a quasi-isomorphism of complexes, so it's an isomorphism in the derived category. Okay, and in particular, what looks like now, this map looks like it wouldn't be invertible normally as a map of complexes, right? But in the derived category, there is a map that's the inverse of this map. Okay, so there's a map from this complex to this complex when we view them as morphisms in the derived category, which is now something that's interesting. Okay, so there is a map from here to here. Okay, so now let me do something else. So here, what I'm going to do is I'm going to make another map here, V. Okay, so here, so what I'm going to do is, again, I'm constructing this map to the twisted version. So this thing here, what I'm going to write down is V1. Okay, so here so normally, to take V, we do it concentrated at degree 0 here, right? Here, but since we're going to shift it over by 1, okay? Okay, so now it's shifted over by 1, and now we're going to take this down like this. Okay, so we have this map 0, 0, 0. Okay, and so here, if we invert this quasi-isomorphism to here, and then we have this map from here to here, this clearly gives us this. So this is this complex V1. So by taking the composition from here to here, this gives us a map from. So we had this extension, right? This gives us an element of HOM from H. So this is, remember, this is the complex concentrated in degrees 0 here of just H. So this is the identification with H to V1. So this is the shifted one. And yeah, this is how we did it. And so we actually took this. This shows you how to hook up a map from an extension of H by V to a morphism in the derived category. Okay, it turns out that this is an isomorphism, and that it doesn't depend on the choice of extension, things like this. Okay, so the claim that we had was true. Okay, so in general, derived categories are going to behave a bit nicer. So let me say some other things about derived categories. Okay. So let me give you a description of the morphisms. I'm going to be building towards a description of the morphisms. So this is so building towards a description of morphisms. And now again I'm going to have to do the bounded derived category, or sorry, the not bounded but the positive. So we just have positive pieces. Okay, so we need to talk about injectives. Talk about injectives. Okay, so let's recall a definition. So A has enough injectives if for all objects in the category A, there exists a magic object A in, so let's say in J. So these are going to be the injective objects. So again, injective objects have this guy being an exact functor. Okay. So this is what injective is. Okay, so there exists a magic guy and a monomorphism from A into the magic guy of A. Okay, so I say magic because this is highly non-constructive, but we're going to assume that these things exist so that we can apply some magic to get injective objects like this. Okay, so in particular, from now on, what I'm going to say is not computable, right? So unless you have an injective resolution, this is going to be really not nice to put into a computer. Okay, so let me say some facts. Okay, so suppose A has enough injectives. So suppose this category A has enough injectives. Okay, so then the first fact that we can do, so then claim. We can find an injective resolution of A, an element of A. So for every A, we can find an injective resolution. here we're going to have a map like this to I0, and then we have I1, I2. Okay, and so this part is going to be an exact sequence. So this is exact here. An exact sequence here. Okay, so this is claim 1, I guess. So let me talk about the basic strategy. So maybe this is familiar to everybody, but let me just say it again. So the basic strategy for this to do this. Okay, so the category has enough injectives. So we take A, then there's an injective object I. Okay, it's an abelian category, so we can do we can look at this let's say, sorry, not A. Oh, I guess we can call it A. We'll identify A with a subject. But normally this would be the image of A, but we can just do this, okay? And so we have this, so we have this injection, and then we can take the quotient, and now, okay, so this guy here is magic, what I call the magic guy associated to A. There may be many magic guys, but we're just going to fix one guy, okay? So then what we can do is we can apply magic again, and we can stick this guy injectively into this guy here, like this. Okay, so then the first step, okay, so then we have the first step. Okay, so this gives okay, so or the second step, I don't know, depending on what you want to call this. Maybe this is the 0th step. This goes here to I, and this thing goes to magic I mod A. Okay, so here, maybe this is I0, this is I1, or maybe we'll do superscript since we're doing a complex like this. This is I0, I1. Okay, and then you kind of continue like this. So here I'm gonna take the, I look at the co-kernel of this, and then I take the magic guy associated to the co-kernel, and then I slap that on here. Okay, and I keep going. You continue like this, and then check the properties. Like you check exactness. Okay, so let me give you another claim. Okay, so fact 2, claim 2, okay, which I'm not going to prove, is suppose that Q from A bullet to B bullet is a quasi-isomorphism. Okay, so suppose we have a quasi-isomorphism, okay, like so. If B bullet is built from injectives, so every one of those guys is an injective guy, then so there exists a morphism F from B bullet to A bullet, okay, such that so F, so we apply Q and then we can apply F, and so this will be homotopic to the identity on A bullet. Okay, so there's actually this is homotopic to the identity. Okay, so also I say let me make something else here. Here, so it's necessary to work in with complexes where so again, these are complexes where you're going to be 0 when you have negative values of I. So like the negative, so here, i.e. So i.e. this. So what I'm going to say this is that k of let's say negative I is equal to 0 for positive I. So when we take negative, the negative cochains are going to be 0. So things in negative degree are going to be 0. Okay, so this is what we have. So this is something that you can do. Maybe I'll put a reference in the comments or in the description. Okay, so that's that. Okay, so let me give you. So we have these two things about categories with enough injectives and these complexes. So okay, so let me say this. So corollary of 1. Okay, so people always say that that an object is quasi-isomorphic to its injective resolution. Okay, so suppose A is an element of A. Okay, and so then and let I 0 to I1. So this thing here, 0. Be an injective resolution. Then, as complexes, A is quasi-isomorphic to this complex here. I bullet. Oh crap. Let's do 0, 1, like so. Okay, so we're going to do superscripts in the derived category. Like this. Okay, so we have a quasi-isomorphism like so. And indeed in the derived category too, without the plus. Okay, so this is saying, this is the statement that an object is quasi-isomorphic to its injective resolution. Okay, well, let's say this. Let's do this again. Okay, so let's do the proof. Okay, so we need to construct a map, and we need to show that they're quasi-isomorphic. So again, A, as we said before, is identified with its complex in degree 0. Okay, and now we have I0 here, I1, I2, etc., like so. Okay, so we have this map here. Okay, and it goes on. Okay, so we have this complex, this is A, this is the complex I bullet, this is the complex A, this is degree 0 here, okay, and okay, so we have this map here, and now we just need to show that this map induces the same cohomology. Okay, so let's look at first of all, this complex here is easy to compute. A0. So this complex here. So this is just A, and then HI of 0A 0. So this is equal to 0 for I not equal to 0. Okay, so this is the computation of the first thing. The second computation, so H0 of I bullet, this one's the trickiest one here. So, but it's not so bad. So Z0 mod B0. Okay, so Z0. Okay, so how did we, so let's recall about how we constructed the injective resolution, or the remarks that I said before. So here, from this one to this one, well, what we did is we took the co-kernel of this map, right? So we did I0 mod, so I0 mod A, and then we took the magic guy, so the magic injective object associated to that, and that was I1. Okay, so in particular, from here to here, the kernel of this map is going to contain A. So it's actually going to be equal to A. And we're identifying A with a subobject of I0. Okay, and so now the boundary, so the boundary is here, right? So here we have just 0. So this is equal to A. So this is nice. This is already, we can already see this is nice. Okay, and HI of I bullet, this is 0 by exactness. Okay, so we're using our description of the injective resolution that we had before. Okay, so again, we conclude that A is quasi-isomorphic to its injective resolution. Okay, so that's the motto, right? Not the well, this is the statement. Okay, so this is what we mean. We mean by we view this as a complex, and then we take the morphism here to be like this. And sometimes people write it like they write it like this. Okay, and so for me, it's a little bit confusing because you don't know if like you're supposed to be looking at a complex like A like this, or I don't, you know, but you're really supposed to be doing it like this. Okay, but this is the notation people use. Okay, so I said that we were going for. I said that we were going towards the description of morphisms in the derived category. Okay, so okay, so let's let of morphisms in D plus of A. Okay, so now I'm going to use in this. So since I fixed this, I'm really going to use the part that that the 0 parts are so the negative degrees are going to be 0 for the complexes, and I'm going to do this so that I can apply that fact that if you have a complex, so you have a quasi-isomorphism of complexes where the target complex is built by injectives, meaning that each object is an injective object, then there exists a cochain map going from what was the target to the source, such that the composition of the two maps are homotopic to the identity. Okay, so I'm going to use that in a strong way. So so here, so some notation. Maybe I already used this before, and I'm sorry for not introducing this again. So these are the so this is the same category A, but this is same category. So this is just the injective objects. Of A. Okay, so it's like the same category where we just restricted the injective objects. Okay, so now what we can do is we can consider. Okay, so theorem. Okay, so we have these homotopy categories. Okay, so homotopy categories are just cochain complexes, right? And those are the objects, and the morphisms are cochain maps up to modulo homotopy. Okay, so we can consider okay, we can consider this the complexes with built from injectives, okay, up to homotopy, and this goes into here. Okay, and then from here, from the homotopy, we have this localization into the derived category. Okay, and it turns out that this, so maybe I should say K plus. Okay. So it turns out that that this from here to here is an equivalence of categories. Okay, so we have these injective complexes, so where the negative degrees are 0, and then we have all the complexes where the negative degrees are 0, and then and we claim that this is an equivalence of category. So the composition blah is an equivalence of category. So the proof. Okay, so we have to use a slightly stronger statement than we said before. Actually, so there's kind of like a lemma. So for all k, an element of, let's say, k plus of a, so there exists an I in k plus of inj of a, such that k is quasi-isomorphic to I. Okay, so these two guys are the same. So like every complex is quasi-isomorphic. A complex of injective objects. Okay, so here what this is saying is that this map is essentially surjective. So this is essentially surjective. Okay, and the other part of the proof so the last part of the proof uses claim 2, that i.e. that all quasi-isomorphisms. So if we have quasi-isomorphism, so where this is built from injective objects, let's say F, there exists a G from I to A such that F composed with G is homotopic to the identity on A. Okay, so again, like we can look at morphisms in the derived category, and all those morphisms are going to be, when we look at injective objects, are going to be represented by morphisms in K plus inj. Okay, so this kind of describes how to look at morphisms in the derived category. I hope you enjoyed this video. Thanks for watching.